This is a presentation on a paper on educational robots and computational thinking, written by Dave Catlin of Valiant Technology and Dr. John Woolard of the University of Southampton. I'm Dave Catlin and I presented our paper at the Educational Robotic Conference held in Padua, Italy on the 18th of July 2014. In 2006, Professor Jeanette Wing from Carnegie Mellon University made the statement that the way computer scientists and computer programmers think is so universally applicable across all subjects that it's something that should be taught in K-12 schools in the same way that we teach reading, writing and arithmetic. She really caught the zeitgeist of the time. In England, where people are disenchanted with the ICT curriculum, well, that's gone. It's been replaced by a computing curriculum where the focus is on computational thinking and programming. Earlier this month, Singapore made a statement of intent that they were going to adopt the same strategy. All over the world, computational thinking projects are taking place. Curiously, one or two commentators mentioned, well, we used to program in the past with things like Logo, but then we stopped and started using little packages, etc. When I first heard this, I thought, hang on, I've been involved in educational robots since 1983. Programming has never stopped. In fact, in 1998, when the national curriculum was introduced in UK, the use of programmable toys and control technology was embedded in the curriculum, and it has been ever since. When I got over myself, I realised actually this was a fantastic opportunity to promote educational robots. The computer scientists are still debating about what this means, how they're going to implement it, etc. And one or two of them have mentioned in a sort of offhand way, well, educational robots is one of the areas that could prove quite useful. So what is computational thinking? What are its objectives? Where is it going? What is it trying to do? And how are educational robots going to play a role in that? Does the history of educational robots play any part? Well, educational robots started with Seymour Papert when he invented Logo and the turtle robot as an object to think with. Here's a piece of Logo code, and when a student writes this, they're going to make the turtle draw a square. But you'll notice that in doing that, they're describing the attributes of a square, but even more, they're having to dig deeper into the underlying structure of polygons. Now, one of Papert's inspirations was the work of George Polya, an Hungarian mathematician who was teaching in Stanford. Very bright mathematical students, quite capable mathematical students, but they had something missing, the X factor. They did not think like mathematicians, and Polya addressed this. So he was one of the first people to say, in fact, the first person to say, it's not enough to know the facts, but you also have to be able to think in a particular way. Well, that's exactly what the computer scientists are doing. Here is a list of what they say are the characteristics of computational thinking. I mean, the list is still under debate, but when you look at it, the idea of abstract thought, for example, is quite clearly something that is universally applicable across all disciplines. That's a difference between the work of Polya and the computational thinking. Polya was concerned with mathematics, computational thinking is across all subjects. And that's led to a number of people being incredibly zealous about it. We've found the holy grail that will solve all educational problems. And wiser heads like Hemmendinger has said, no, hang on, these other subjects have all got their own claims to things. Mathematicians, for example, have a claim on abstraction long before computer scientists ever existed. And in fact, computer scientists are not the first group to make this claim of universality. The design technology movement have been making it for decades. Everything that's man-made is subject to the design process, whether consciously or subconsciously, and that includes all computer programs and all computer systems. Ron Todd's Project Update, for example, was NSF funded. It ran across 6 states and its objective was to deliver STEM subjects through design technology process. Now, as a design engineer, I can tell you I was completely zealous about this until I had a very salutary experience, and I went into Montgomery County in Maryland, and I tried to persuade the science coordinators there that this was a good idea, and they made it very clear to me that they wanted their students thinking like scientists and not designers. Well, the work of Lav and Wenger on communities of practice have shown that this is not some silly little turf war. To be a mathematician, to be a scientist, to be a midwife, you need to adopt the practices and thinking processes of that discipline. And while there's a lot of commonality between them, there are also subtle differences. Now, the computer scientists will quite rightly say that yes, but computers are applicable across all disciplines. Well, communities of practices are not static. They are dynamic, ever-changing, and certainly technology, something as powerful as a computer, will change pretty much all of them. But the important thing is that the change comes from within the discipline and not externally imposed. Fellison and Krishnamurthy have cottoned on to this and have suggested that computational thinking should be delivered within the core subject of mathematics. Now, their critics have criticised them and said, well, really what you're doing there is hiding the light of computational thinking under the bush. To which they responded that this wasn't a theoretical position, but it was based upon their practical experience of trying to deliver computational thinking through their outreach programs. Well, this is something that educational robots have already resolved. They have decades of practical experience in classrooms delivering computational thinking and programming throughout every single subject in the curriculum. More than that, they have a proven track record from preschool to grade 12, from slow learners to the best of the gifted and talented. They work with different genders, cultures, ethnicities, and even if we just look at the Valiant products, this has been done in 30 different countries. Well, now it's time to look at robots in more depth. And to do that, I'm going to use the ERA principles, which is an empirically derived framework used to analyse the value of an educational robot and its activities. And I'm going to apply this framework to 2 activities. The first of these activities, what did I do, is for preschool and kindergarten children. All they have to do is press the go button and the robot runs off and does its things. It moves forwards, backwards, turns left, turns right, waits, plays a sound, etc. The children's task is to describe what they see. Now, at this age, they will not have the language to do that, so their imagination has to kick in. They start discussing various ways of describing what they see, and with the help of effective questioning from the teacher, they'll start to gain knowledge of some very basic concepts. The first area principle we're going to look at is the embodiment principle, and that means that the robot is a physical robot. It's not a virtual robot on a computer screen. The problem with the computer screen robot is that forward could be up, it could be down, to the left, to the right, whereas with the real robot, it is forward is the same for the child and the robot, right is the same for the child and the robot. And this makes things much more tangible, much more practical. The second part of this is the interaction principle. We learn and gain meaning from the world through what's called a semiotic process. And in this case, the semiotic process is the mathematics of space and the mathematics of movement, like position, forwards, left, how far forward, how far left. It's also about sequence. When you analyse a number of activities, you begin to see a set of characteristics appearing time and time again. We group these together in what's called the pedagogy principle. Now, this particular activity is classified as a catalyst because its sole purpose is to provoke a discussion. The students will also engage in computational thinking skills in terms of abstraction, algorithmic thinking and decomposition. However, notice that no programming is involved. Now, this is a debate amongst computer scientists. Does computational thinking necessitate programming? Well, clearly that's not true. A system analyst, for example, will be involved in computational thinking, but will not necessarily be involved in programming. Mastering computational thinking is an internalization process. It becomes a natural thinking pattern that we use consciously or subconsciously, not just with computer programming, but in a variety of situations. It is an example of what we call the sustainable learning principle. That is, it is a lifelong learning skill. Now, not always, but generally, computer programming is a solitary affair, whereas using robots is usually done in groups. And in this way, it doesn't just develop cognitive learning skills, but it also develops social, emotional, and personal. This brings us to an interesting point about implementing computational thinking in schools, particularly primary and elementary schools. Computational thinking is the thinking patterns and practices of expert computer scientists. The success of teaching these thinking strategies has been very mixed. Professor Ian Stewart points out that George Polya was an expert. He didn't have to follow a checklist of things to do. To him, the thinking skills that he was talking about were intuitive, and he was very flexible in the way he used them. An advantage of approaching computational thinking through robots is that there is already a large body of teachers out there who in reality have been engaged in computational thinking with their students for many years. All that's required is a change of perspective and a change of jargon. We'll briefly look at one more activity, in the doghouse. In this activity, the students have to make Roma into a dog. They have to create a path for the dog to walk in. They have to study how dogs behave. They have to make a mathematical model of that behaviour, create the algorithms, and then a program. This is a very cross-curricular activity involving lots of different subjects, and notice there's a good correlation between the tasks and computational thinking skills. It also emphasises a point made earlier. This activity is from our archives. It was first done in 1985. It also illustrates two of the era principles. The curriculum and assessment principle is really about activities must help teachers deliver the curriculum, and this particular activity does in a number of different ways. And that's also part of the practical principle, because what we're about is getting teachers to buy in. We must make things easy and simple for teachers to do. So let's summarise. Computational thinking is taking place in a lot of different countries. There is a practical need for activities that work and that are tried and tested, and there is also a practical need for working within different subjects. Educational robots have a long history of already delivering computational thinking into K-12 education. They have a substantial bank of tried and tested activities that integrate computational thinking into different subjects. And there's also a group of teachers who, although they may not be familiar with the terminology, are already familiar with the technology and the processes. So to conclude, I think there are strong synergies between computational thinking and educational robots, and it would benefit both communities to find ways to work together. Thank you.